So last time we learned about martingale, and then we proved this Azuma's inequality. So in order to prove this Azuma's inequality, we need to check this condition. And many times we are using this exposure martingale that we defined last time. And now we want to check whether some given exposure martingale satisfy the condition of this Azuma's inequality. So for example, if we have a H exposure martingale and some function f depending on G when G is drawn from G and P, the random graph. And let's say f is a chromatic number. Then every H change, if you change one H on here, so let's say G and G prime are the two graphs which differs on only one pair. There is IJ which is in G but not in G prime. And every other pair has the same adjacency and not adjacency. If these two are differ by 1, then we want to show that our martingale, H exposure martingale that we defined last time, this satisfies this inequality. So that's our goal to prove. So let's prove it in more general sense. Let's say omega is a to the b with a set of all functions from b to a. And we define a measure by, say, fixing values PAB and setting the probability that GB is A is PAB. Of course, this PAB has to, for fixed B, if you vary A, then it has to be 1. So that for each value in B, for specific value B, GB could be 1 over A. So it's chosen from A with the probability each of them being PAB. And where the values of GB are mutually independent. Meaning that B and B prime, G of B is say A, but that does not affect the probability of this being A prime. So this event and this event are completely independent. And we fix a sequence of sets which is called gradation. Say B0 is empty and you have B1, B2, and Bm. So in our application here, you can consider the set of all the pairs to be B, and then A is either 0 or 1 depending on the adjacency. And this is P. PAB is when A is 1, it's P. When A is 0, it's 1 minus P. And now in here we are ordering the edges one by one, and that defines this martingale, and that's reflected here. So this is set of E1, and this is set of E1, E2, and so on. So Bi is the collection of random variable we fix here when we define this exposure martingale. And let L be the function this is, this L. For each of this function, we assign a real value. This be a function, and for each, say h in this function, we define a martingale x0, x1 to xm with xih is the expected value of Lg when G is randomly chosen. So a function h is given. Let's say it takes value like this, and then let's say you consider x3h. Then you, each of them, let's say each of them is y1, y2, y3, y4. No, that's first coordinate, second coordinate, third coordinate. This is the expected number of value of Lg, where g of 1 is 0, g of 2 is 0, g of 3 is 1. Technically, in order to define this, we only want just I values. I first coordinate. The later one is not relevant, but writing this way would help us to write things in more compact way later. Then when G, so this defines this martingale. You reveal one coordinate at a time. Then this is written in this way with the h, but if you reveal I coordinate, then this is well defined, because if I coordinate is fixed and then later one is whatever later one is, you can define this with the same value, this expected value. So this defines martingale. So let's define that for a vector C. Let's write this way. C1, C2 to say Cm, and we say that a function L satisfies C-Lipschitz condition. Relative to the gradation say P0 and Pm if the following hold. So for each I, we have that if H and H prime differs only on Pi plus 1 minus Pi, so again P1, P2, P3, and so on. And each of them, these are in B, and for each of them we define the function value. Say A is 0, 1, 2, 3. And once we change one of these, then the L value changes. And then that changes, so if we change one of them, then the L value changes n mod ci. So whatever you change this to other number, then this coordinate and this coordinate yields these values of L. Those are not, not too far. Then you say this is C Lipschitz. And when you say the C Lipschitz for a single constant C, it means it's a C, C, C Lipschitz in our notation. And we simply say Lipschitz. Then this is one Lipschitz. So now we have set up this. In this setup, it's more general than what we actually wanted at the beginning, which is for the random graph setup. So H exposure martingale can be considered as each gradation you add one H. But the vertex exposure martingale is, each time you add all the H's incident with the specific vertex. So this also generalizes both, of the vertex and H martingale, H exposure martingale. So with this, we can prove this. So that L satisfies the C Lipschitz condition relative to the gradation given, then the corresponding martingale defined as above actually satisfy the condition that we wanted. So this is for all possible H. So this measures the possible difference between these two on all cases. So this is exactly what we wanted. So let's prove this. So let G be a random function drawn from A to the B according to the measure, of course, according to the measure defined before. And let's define some terminology so that later we can consider the proof with this notation. Let's say, so H is given. And we want to show that for this H, we have this for all I. So we consider all the H prime, which has the same value with H on Pj, and we write it as Hj. So we have this gradation. Say you have a pi plus 1 and pi. Then hi is H is already 1 0 0 1 1 given, and hi contains all the function which have the first 6 coordinate this and then later one arbitrary. Then what do we have this? For this h, if you consider, I plus 1, so this value, give me a moment, let me check one thing. So this is as our definition, expectation of L value, conditioning on the values on here. So you consider all the L value with the probability that G equals this H prime, assuming that the G and H has same value for all B in Bi plus 1. Let's shorthandedly write this as a W sub H prime. So this is W sub H prime. That's the definition of H, this W sub H prime. And now we want to measure XIH, but we want to write it in a way that we have some summation with this term, and then something else here which can be, related to, which can be subtracted to the L function there. So for each H prime in Hi plus 1, we let H bracket H prime be the collection of all functions which has the same value for all B not in Bi plus 1 minus Bi. So when H prime is given, say 1 0 0 1, zero, 1, 2, 0, 1, 0, 1, 1, 0, 1. Then you can consider, you can keep this value and this value, and you can change these three values into arbitrary one. Then that's the collection of, this H bracket H prime consists of all those functions which have these 6 and these 4 coordinates, while these 3 coordinates are arbitrary. Then now we write xi of h. Again, this is by the same way. You take the L value, multiply with the probability that the random function g is same with this h double prime, given that its first coordinates are same as h. Now we want to rewrite this in a way that we want to see this summation. So we consider all the h prime in hi plus 1, meaning that first this is fixed and then these are arbitrary. But this one is that this is fixed but these are arbitrary. But now we want to change this to the sum that these are fixed but these are arbitrary. But we want to somehow, make sure that this can be also some other things. In here, these are, just fixed as same with h. But on here, those coordinates in here are not necessarily same with h. So what we do is we use this. We take h star in h of h prime. So first, what we do is we make this arbitrary. So this can be changed into several terms in here. But by taking this h bracket again, so as we picked before, this is fixed and this is fixed, but now we are letting this vary. So this is the splitting of these two. And again, then this sum becomes same as this. And then this probability also can be split. Again, this is that you first fixed this coordinate and then letting this vary so that you get the probability, but you reveal those conditioning on that. Conditioning on this and you take the expectation of this, but conditioning can be also split. You condition on this and then take this, and then you conditioning on that and you take the remaining value and compute the probability. So this is same as you conditioning on the or first value or the coordinate in bi, and then you compute the probability that the coordinate in here are exactly same as this h star, and you multiply by probability that the remaining one so let's say remaining one is same, that means those two are exactly same. Conditioning on all the things on bi plus 1 is same. Then now we want to claim that this and this with this h prime are same. Because what does this mean? So this is g equal to h prime, gb equal ghp for all p in bi plus 1. And what is h prime? H prime is, let's give me let me copy this. So h prime is taken from hi plus 1. That means when we have initially h is given, and hi plus 1 is as here, so H prime must be chosen from before so that all these coordinates are same. And this could be some arbitrary one. And H bracket H prime is the one that these coordinates and these coordinates are kept while this could be different. That means these coordinates are exactly this. So what you know is that H star B equal to H prime of B for all B in this outside. So what we know is that each of these coordinates are mutually dependent. So this is exactly saying that the probability that we get 0 here, 1 here, 1 here, 0 here. So that's this probability. And what's, because H star is again, this could be different, but these and these are same. But with this definition being WH prime, what's the WH prime? That's exactly the probability that the conditioning on these values, now you compute the probability that you get 0, 1, 1, 0. But as these random variables, these values are mutually independent. So what happened here is not important, but what you get here is 0, 1, 1, 0 is important. So both of this and WH prime indicates that you get 0, 1, 1 value here. So this later one can be replaced with WH prime. And let's write Q H star with this probability that when you fix the first I value, first values in PI, the probability that you get the middle one as H star. Give me a moment. So if you rewrite this entire one with this new definition, then XIH is summation of H prime in H sub I plus 1 and H star in H bracket H prime, L H star, QH star, WH prime. Then what's this? Now we also collect this summation, first summation, and then LH, WH. Then that's summation of, you just take the first summation and you take the LH prime. This is coming from here. And the later part you sum, you might take the minus. You take this. So you take this and then, put it out, which is here, and then later term is here. Then this is summation of H prime in, say, I plus 1. So this can be rewritten in this way. But the H prime and H star, because of this H bracket definition, they are only different on these coordinates. And the Lipschitz condition is that exactly saying that this value is M of Ci. So this value is M of Ci. And now we have summation of H, WHI and summation of H star. But the QH star is defined to be this. So for all BI, it's fixed. And then now BI plus 1, the remaining coordinate, you vary. But that's exactly what this is doing. So if you take the QHI, then this is 1. And again, H prime varies over H sub I plus 1, which is defined in the way that all the I plus 1 coordinates are fixed and then later are changing. So that's the definition of H sub I plus 1. And probability of this is you fix the I plus 1, P sub I plus 1 and take the probability of the later things changes. As this definition allowed to change vary over all possible things here. This is again 1, so this is M mod Ci. So this now finishes what we want. So now with the Azuma's inequality and this, if L satisfies, say, C Lipschitz condition relative to gradation, then for all lambda, we have that the probability that L of G minus its expectation is bigger than lambda is smaller than 2 times exponential to the negative lambda square over 2 summation I Ci square. So we obtain this. So now in the next video, we will consider some application of this to easy problems. Not just easy problem, but some easy problems and as well as some more complicated problems. So which we use this to solve some combinatorial problems.